We are recording. We are live. Welcome to Mr. Mac's review session. Brought to you live on this day, December 17th, 2022. So, quiz one is this one. For our live studio audience, would you like to see either of these first two on the first page, or are we good on those? Okay. Zoe, are you set? Okay, cool. Then we will skip over them. And if you have those check marks, you probably have check marks in 522. And 531 is different because it's elimination. Do we need to see elimination? No? Probably not. Okay, cool. Tweedledee, Tweedledum problems. 541. Parents started a small farm. So all the basics are taken care of on those quizzes for everybody here in our live studio audience. Wonderful. White, crooked. This is nuts. Okay. This. Okay, that's better. All right. Intermediate. These guys. So this is 521. No. Okay. So let's talk about it. So, unfortunately, when we teach algebra, we basically teach it in order to just get you through it. We don't actually teach about strategizing and how we can make problems easier. It's just like, do this to get the answer. And you get through it, and that's great. But the problem is when you get stuff like this, right? This is super gross looking. However, if you know some strategies and tactics to be able to handle a problem like Maria, it's actually not that bad. So we really hate fractions, right? They're awful, god-awful, ew, gross, disgusting. But what have I told you? And again, this is for you guys in the audience and for people that might be watching this later. We could get rid of them, right? This is just divides by 18. That's divides by 9. That's divided by 6. And you might remember from Algebra 1 that you can times everything and get rid of division, right? So let's do that. When you multiply or divide, you have to do it to every single term. You can't just do it to one of them, right? Adding and subtracting, you do it to both sides. Multiplying and dividing, you have to do it through every single term. So we could multiply by 6 to get rid of this. Divides by 6. Now, conveniently enough, there is a single number that will get rid of all three of these, and it's 18. So if I times everything by 18... what ends up happening is the following. I use like. So we times by the top, divide by the bottom. And you should divide first if you can. 18 divided by 6 does work out. And again, this is why 18 gets rid of all the numbers, because 18 is divisible by 6. You get 3. So we've got negative 3s coming out of that, right? 18 divided by 6 is 3. 3 times negative s is negative 3s. Then 18 divided by 18 is 1. 1 times 25 is 25. Don't lose your equal signs. I definitely will multiple times today. 18 divided by 9 is 2. 2 times 4r is 8r. And that's a way better looking equation than what we had before. The same thing can be done on the bottom here, except instead of maybe multiplying by 18, we could multiply by 8. And 8's a good number because it gets rid of this 8, it gets rid of this 4, it gets rid of this 2. So I'm going to do that. Make it look nice and neat. And I'll use a different color for this equation. Hopefully green shows up. We get negative 3r here because 8 divided by 8 is 1. 1 times 3r is 3r. Don't forget your negative sign. Then we have 8 divided by 4, which is 2. 2 times 3 is 6. Again, negative. Then we've got an equal sign. 8 divided by 2 is 4. 4 times negative s is negative 4s. So far, so good. We feeling great? How's our live studio audience? Woo! Laugh track. Yeah. Okay, awesome. Phenomenal. I have a soundboard over there. I just didn't have time to hook it up. It would have been fun. I have lots of Michael Scott quotes pop up. Anyway, so here are two equations, and I'm going to include the squiggle just for Zoe. These two equations are related, meaning that s is the same as that s, that r is the same as that r, meaning if you find r in one of them, you find s in the other as well. So, what do we do? Well, I think we should use substitution because I read the directions, unlike Zoe. So we're going to use substitution, called out. We're going to use substitution. So I'm going to get one variable on its own. And then we're going to plug it into the other equation. So I'm going to choose the top equation to get r on its own. I don't know. Just seems like what I feel like doing right now. R is really close to being on its own. All I got to do is divide everything by 8. Again, when we multiply or divide, we do it to every single term. So when I divide negative 3s by 8, I get this. When I divide 25 by 8, I get this as well. They have the same denominator, so why not just put them all over 8? Right? That whole thing over 8 looks beautiful the way I drew it. And that's what r is. So we're going to take this and plug it in for r down here's. We plug it back into itself, we'll get something that is true, like 7 equals 7 or 0 equals 0, which tells us, hey, the equations are the same. except they aren't. It's just you plugged it back into itself, so of course it's going to tell you it's the same equation. For those that know, no, I'm not going to explain further than that. So let's get here, and let's plug in for r. Whenever you plug something in for a variable, shout out to Brock, we always wrap it in parentheses. So we're going to do this and leave a space for it. And I'm going to plug it in color because I am that girl. So negative 3s plus 25, y'all over 8. Cool, 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 cool. All right, now, once again, to get rid of division, we can multiply everything by 8. That's not too scary. The numbers won't get too big. We can see all this. And we're going to distribute that 3. So I'm going to do both at the same time. So hang on to your butts. When I distribute this negative 3, I get positive 9s, and I get negative 75. And I'm going to times everything by 8, so I'm not going to divide by 8 anymore. So I'm timesing by 8. That's going to get rid of that. After I times everything by 8, I end up with, instead of negative 6, I end up with negative 48 equals another negative number. 4 times 8 is 32. Shout out to Eli. So this is what you get. So I distributed the negative 3, and I times each term by 8, and now I've got this, which is one equation with one variable, meaning we can get s on its own and it'll equal a number. Hooray. So let's do that. I've got 9s, and I've got this put together. Negative 75 minus 48. Well, if I take away 25 first, I'm at negative 100. That leaves me with 23 left over, so I'm at negative 123. And if I make a mistake, please call it out. Perfect for 3 hours straight over days. Get that out of my hair. Now we have this. I'm going to get my s's together and get negative 123 equals, subtracting 9, I get negative 41s, which actually just come out nicely, right? If 41 were to go into 123 evenly, it would go in about 3 times, right? Because 40 times 3 is 120, and 3 times 1 is 3. So, yep, it'll work out, and it'll be positive 3. So if we divide both sides by 41, negative 41, we get s is 3. How you feeling? These or not at all? You did. Yep. You get really nasty numbers, and I went home and checked it, and guess what? They come out nicely. So there is one problem, if not 2 on here, that does come out not nice. Oops, sorry, but that's just the breaks, kids. Sometimes that's how it is. So s is 3. Cool. Well, if s is 3, I can literally plug in 3 for s anywhere and get r. Assuming we did our work right up here, why not just plug it in there? Because then when we plug it in and do the math, we just get r, right? I mean, assuming we did this right, it should be fine. Let's do that. So I'm going to take negative 3, plug in s. Again, we wrap it in parentheses whenever we plug it in. Plus 25 divided by 8, and that'll give us whatever r is. So I know, if I get myself out of the way, that 3 is s. Cool. So I plug that in. And now I'm going to get negative 9 plus 25. That's the same thing as 25 minus 9. So take away 5, take away 4, I get 16 over 8. Oh, that's nice, because that means r is just 2. Winner, winner. How you feel? These? Fabulous. Okay. So the big brain play here is actually not, can you do substitution? It's more so, do you know what to do when something's really nasty? Mess with it until it's not, right? Make a harder problem into an easier problem. And that's one of the lessons that we really need to learn in this math class, is that difficult problems are just easy problems in disguise. You just have to look at them in a different way. And by timesing everything by 18 and timesing everything by 8 in the bottom, we get much nicer equations. So the same theme is going to be down here for part D. If I do this, how is that really what? Okay, so here, decimals. Awful, terrible, right? But what if I told you that that's just 2 over 10? Well, you know what to do up here, right? When we have like over 6, we times everything by 6, or times everything by 18 or something, right? Well, this is 2 over 10, so why not just times everything by 10? Now hold your horses. This is 3 over 10, but that's 2 over 100. So it seems like it'd be better to times everything by 100 rather than 10. That'll get the job done super quick. So let's do that. Let's times everything by 100. And so, I mean, by definition, if you're getting rid of fractions or decimals, you're making them into bigger numbers, right? Like, that's why they're gone. Otherwise, they'd still be fractions and decimals. So While we will get rid of nasty numbers, we will get big numbers, so watch out for that. After we do that, we end up here. If I times by 100, that moves the decimal place over twice. I get 20y minus 30x equals, that moves the decimal place over twice, so I just get 2 minus 2y plus 9x. That's not all in frame. I'll zoom out a little bit. Hopefully that's, can you read that? Is that okay, people in the audience? Yeah? Okay, cool. I'm trying to write tiny because if I write really big, I'll end up with Zoe's problem where she runs out of room in like 3 steps. Yep, I know. So the bottom, I can just get away with timesing by 100, right? Because I only need to move the decimal place over once. So, and by 100, I mean 10. I don't have the times by 100. I just have the times by 10. That'll get the job done. And I'll end up with this green equation, which is 12y plus 10x equals 6y plus 7. Cool. So I'm going to take that blue equation and green equation, clean them up a little bit, just so they look nice and they're more condensed. So I'm going to get my y's together. I will add 2 y's to both sides. That means I've got 22 y's on this side. I'm going to subtract 9x to this side, so I get negative 39x's. And then I'm going to just leave that equal to 2. And then my green equation, I'm going to clean up a little bit as well. I will subtract 6 y's from this side, which gets me 6 y's on that side. That's nice. 10 x's. And that'll equal 7. Now, what do you notice about the green? Oh, well, actually, no, darn it. Almost everything is divisible by 2. Thought that'd be nice to divide everything by 2 to make it a little bit simpler, but nope, that's 7, right? Oh, 7. So now we got this. Same idea, we have to use substitution, so which was what I would recommend. Trying to get these to match by multiplying would be a disaster. Tell me how, Zoe knows. We are going to get a variable on its own. So why don't we get, I don't know, let's get y on its own. That seems appropriate. So I'll take this, and I will basically just subtract 10x from both sides and divide by 6. Now, I did that all at once. That's kind of scary, but are you following what I'm saying? Subtract 10x, divide everything by 6. Boom. There's y. Are we okay with that move? C. Thumbs up. Okay. So if that's what y is, I'm going to plug it into the other equation, the blue one. Okay? For those of you that are colorblind, I'm sorry. Zoe, speaking of which, are there certain colors I should avoid? Okay. Oh, got you. So they were pointing at stuff like this and being like, Zoe, you don't know that that's pink? Because that's not... Okay. So I'm plugging that in for y, and you'll notice now I have an equation just with x in it, which is the whole point, because if I have one variable in one equation, I can just get that variable on its own and get a number for it, which was the idea. Now, spoilers, I think this one comes out nasty, but we're going to show you what to do when things come out nasty. I'm going to like triple check to make sure that the last version of each quiz doesn't have nasty numbers. That's what I'll be doing Monday night probably, other than tutoring online. But sometimes it does happen. And it will happen more frequently as you get higher in math, and that's just how it is. But yeah, so first thing I'm going to do is I'm going to notice that I can't divide 22 by 6, but 22 divided by 6 does come out to a nice fraction, 22 over 6, which means I could rewrite that as 11 over 3. So I'm going to do that. So I'm going to do 22 divided by 6, and I'm going to get 11 over 3. So that's going to turn this 22 into an 11. And the 6 into a 3, 11 over 3, because you're allowed to divide or multiply in any order you want. So instead of multiplying 22 to everything, yikes, really big number, I will divide first and get 11 thirds. Yay, that's better, because now when I distribute that 11, it's 11 and not 22. So when I distribute that 11, I'm going to get 77 minus 110x. And I'm going to times everything by 3 in a second, so that divide by 3 will be gone. Over here, I don't need to distribute the 11 to. I just need to times it by 3. So 30 times 3 is 90. 9 times 3 is 27. So we're going to get negative 117x. And again, timesing everything by 3 to get rid of that 3 down there, this will become a 6. Get my x's together. Negative 227x equals, subtract 77 from this side. Well, if I subtract 6, I get 0, and then I've got 71 still to subtract, so there we go. And now when I divide, I'm going to get whatever 71 divided by 227 is, because those negatives will divide out. I don't believe that comes out nicely. In fact, I'm like 90% sure 71. And there's one very easy task. Figure that out. This is 71 prime. 71 prime. Yep, prime number. So we can't simplify that fraction anymore. So that's just what x is unless I made a mistake. Now, here's the good news. Pretend Mr. Mac did make a mistake up here, algebraically speaking. I said like 5 times 4 was 9 or something, right? I'm not grading that here. What I'm grading is, can you problem solve, right? This stuff, getting rid of these decimals. Do you know how to do substitution? Do you know how to get a variable on its own and switch it out for a bunch of crap, right? Do you solve for both variables? That's what I'm looking for. So even if you made a mistake, not a big deal, which means if you're spending 10 hours on this problem trying to get an exact answer and make it look nice, you're kind of wasting your time because I don't need to see that. It's another reason why you shouldn't erase your work, because maybe what you did was phenomenal. It's just you said 5 plus 4 was 12. Okay? So now I know that's what x is. So let's go and plug it in over here. Because if I plug that in, I just get y, right? So let's do that. And here's what you're going to do when you have a really nasty number like this. Y is going to equal 7 minus 10 times whatever x is, all divided by 6. And we know that x is 71 over 227. Here's what you do in this situation. You circle it. See how there's no x's or y's in this answer? That's what y is. It's whatever this number is. Ta-da. Right? Like, if I leave it like that, or if I simplify it down to like some ridiculous fraction, it's the same thing. It's like saying the answer is 3 plus 4 instead of saying the answer is 7. It's the same thing, it's just a different way of looking at it, right? So why not just leave it like that and save yourself the heartache? Done. That's it. That's it. How do we feel about this? Okay, do we understand what to do when we get a really weird answer? You just literally put it there and look, no more letters, I'm done. Y is whatever that number is, right? If I give you the, like, if you found out that y was the root of 65, that's not a nice number. So you would just circle it and be done. But that's what it is, it's the root of 65. Imagine you found that y was pi. Would you try to write out all the digits of pi? Oh, you would not. You would just say it's pi, moving on. Cool. Or pi plus 2, right? Same thing. It's pi plus 2. Do we need to see this one? This one has a lot of directions, but it's actually really easy once you know what you're doing. So you don't. This is the one where it either is the equations are literally the same or they're different. So I'll just point that out real quick. If I times the top by 4, I get negative 28y here. I get 8x. Then I get 64. You'll notice that 8x, negative 28y when I move it over. These do not add to 64, which means these equations are so close, but not quite, meaning they have the same slope. They're parallel. They'll have no solution. 531. More of what we were doing on that other one. If I remember correctly, they're in the same checkbox. So I think we do need to do these. So let's take a look at these. 531 Q2. What to do? Well, again, don't just jump into it. Try to make this problem more pleasant to deal with. So check this out. Check this out. I'm going to do this in 2 moves so you can see a little bit better. First thing I notice is that this number is even. 12 over 7 is an even number because I can divide that by 2 and get 6 over 7, right? So that's an even number. I can divide that by 2. See how this is even as well? It's 2 times something. So I can divide that by 2. Let's do that. If I divide everything by 2 in this top equation, I get negative 6x over 7. And that's one term. We have negative 2 times something. Remember parentheses, and again, you didn't have algebra 1 with me or pre-algebra, but parentheses, what they really do is they say, treat this as if it's one idea. So we have -2 times something. If I gave you -2x, I don't think you would say that there's two terms there, right? It's just one. So this is -2 times something. That's just one term. So if I have to divide every term by 2, I can just divide that 2 out. And so what I get is this, minus, because again, -2 divided by 2 is -1. Oops, equal sign. I told you I'd lose one. And you'll notice again, guess what? Everything's even. So what if I divide by 2 again? You could have divided by 2 twice earlier, also known as dividing by 4, but I didn't want to scare you. So I did it one bit at a time. If I divide everything by 2 again, I get this. That's a -18. When I divide it by 2, I get -9. That's a negative 6y, so a positive 6y. When I divide it by 2, I get positive 3y. And so it's already starting to look a little bit better. I could also divide by what now? Look closely. 3, right? So let's do that. Turns out I could have divided everything by 6 to begin with. That's kind of fun. Or 4 times 6, which is 24. You could divide everything by 24. Let's go down here. And I'll end up with -x over 7 equals -3 plus y. I don't think we need any more division. The last thing I would do is get rid of that divides by 7. So I'm going to times everything by 7 and get -x equals -21, because I'm timesing by 7, plus 7y. And honestly, since we're doing substitution, why not just get x on its own? That means x is going to equal 21 minus 7y. Right, the negative version of x is this, so the positive version of x has to be that. Otherwise known as times everything by -1. I'm going to pause just for a second there for station identification. Hi, this is Mr. Max live stream. You're probably watching. Welcome. Do an ad. See through Mountain Dew. Radioactive. So that's what x is from the blue equation. Let's do the same thing to the bottom equation. We're going to call it the green. That's kind of the theme I'm going with right now. Cool. So what do you notice that all 3 of these terms, because again, there's 1, 2, 3 terms here. What all 3 are they divisible by? 1, 2, 3. All 3 are divisible by what? 3. So let's divide everything by 3 and get -2x over 13 minus 2y equals all this junk, no longer being times by 3. And then what do you notice? Yeah, so we can just divide every single term by 2, and that'll actually make it nicer for us. So that's -x over 13 minus y equals -y minus 1. Yo. Did I goof? Okay. And then, if you notice, see how everything's negative? Negatives are worse than positives, so why not we just make it all positive by timesing everything by -1. Cool. And Zoe might already notice that we have y on both sides, which means if you subtract y, they both go away. Or otherwise, like, you can just ignore them. If I subtract y from both sides, this is really, really nice. I get x over 13, minusing y from both sides makes it go away, equals 1. So let's just turn our brain on for a second. What number divided by 13 is 1? 13. So x has to be 13. You could also figure that out by timesing both sides by 13 to get rid of the fraction, right? But if you just turn your brain on, I think you'll be more confident. So this doesn't, like, this literally just gives us x is 13. That's really convenient. Hooray, good thing we messed around with this. Like, normally that doesn't happen when we do substitution. But for this one, if you mess around with it, you get a variable for free. So if x is 13, guess what? I can go over to the blue equation, plug in 13 for x, and then I'll be able to solve for y. How did the 1 turn into a positive? Over here, I times everything by -1, essentially. Yep, or divided by -1, or however you want to phrase it. Or if you want to think of it this way, I like added y over to this side, added y over to that side, added 1 over to there, added x over 13 over to there. Right, just moving them over by addition would do this, but yeah, however you want to think about it. So now I know if 13 is x, boom, 13 is going to equal 21 minus 7y. I wrapped it in parentheses, but that's mostly organizational. Turns out parentheses are two things more so than do these first, right? They always tell you PEMDAS, do parentheses first. It's more so about saying this is a single term and also organization, right? I clearly plugged that in for x. And so now I'm going to solve. I'll subtract 21 from both sides, and I'll get -8 equals -7y. Did I do that correctly? If I subtract 21, subtract 13, and I have 8 left over, yep, that's true. So y is going to equal 8/7. Assuming I didn't make a mistake somewhere. But seems plausible to me. This is 7ths. If I plug in 8/7 over here, this will become 7ths. Probably a good idea. How are we feeling? Are we what? Nope. But that's okay. A lot of the things I do as a teacher are just so I can say, hey, I did it. Go up or don't. All right, down here. Let's get rid of decimals. You guys are going to be really good by the end of this. It's seeing how to like change the problem around to make it easier. I'm going to times everything by 4. Do you know why? They will be, right? So a noob might say times this by 100, right? And we get 25a. But that would be worse because 25 is big, right? But if I times everything by 4, you know 0.25 becomes 1. And 0.5 becomes 2. And that's because 0.25 is just 25 over 100, or 1/4. And of course, timesing a quarter by 4 gets 1. And timesing a half by 4 just gets 2. So yeah, this will come out much nicer. So we get -1a, or -a. We get positive 2b, or not 2b. Who's to say? And we get -8. Yay! That's pretty good looking, right? That's much better. In the bottom, we could also double stuff because we got 0.5s, right? That's better than timesing by 10, especially since we're gonna have to times by 1,000 to get this on its own. Zoe, how'd you know? So I'm just gonna times everything by 2 first, and then you're gonna see what's gonna happen, okay? So timesing everything by 2, it will not fix our 1.875 problem, right? But it will help, and then you'll be able to see what to do after that. So I'm just going to do it one little bit at a time. This is going to become 21. This is going to become 13b. That becomes 10. This is a tough problem, but we got this. If I double that 5, right, it's going to become a 1. If I double that, it's going to become a 14. So we've got a 5 on the end now, and we add those together. When I double this, it's 1.6, but add a 1 to it, so 1.7. And when I double this, I get 2 plus that extra 1 I carried over in my head. So 3.75 is what we've got there. Don't lose your variable. There's an A. Okay, if you need to sit down or raise your hand and have me double that for you or whatever, I can. But 3.75 is what you get when you double 1.87. And then we've got double of this, which is 15b. Cool. So we still have that 3.75, which is annoying. Did you know 3.75 is just 3 3/4? So if we times everything by 4, that would go away, wouldn't it? Quarters, when you times them by 4, they go away. So let's times everything by 4, and we'll take care of this. So what you're realizing is that 1.875 is really 1 1/8 because we times by 8 and it got rid of it. So that's the decimal version of 1 1/8. Let's do that, and we get 84 plus, for those of you learning at home, 4 times 13 is really easy. It's just 4 times 10, 40, plus 3 more 4s, right? So 12, so it's 52b. And that's going to equal, again, don't lose your equal signs, 40. 3.75 is hard to do in your head, but again, it's 3 3/4, right? So if you double 3, or sorry, times 3 by 4, you get 12. If you do 3/4 times 4, you just get 3. So in total, this is 15. A. And then 15 times 4 is just 30 times 2, which is 60. So now I'm going to get my A's and B's together. I'm going to subtract 52B and get 8B on this side. I will leave the 15A over here. And then I'll subtract 40 from this to get 44. 44, 15, and 8 have no common factors, so there's nothing to divide out, which is fine. They're not that big. Especially compared to Zoe's like 1,875 coefficient. Sorry, I always pick on one student. It was Alex Albano last year. It's you this year, Zoe. So here are 2 equations. I will write the other one down here. That way we can see it. Again, squiggle. Zoe's getting bullied. Yeah, I know. There's not much of a choice, and I like Olivia, so that kind of narrows things down. All right, so here are 2 equations. I wrote the -8 there just so they'd all match up. That's kind of nice. We're told to use either elimination or substitution. If you want to use elimination, it wouldn't be a terrible idea because like timesing by 4 to get the b's gone wouldn't be that bad, would it? Right? Again, the directions say elimination or substitution. I always leave substitution on the table because it's like super transferable to higher levels of math, whereas elimination isn't as much. But you can use elimination, and timesing by 4 wouldn't be a bad idea here because, again, timesing by 4 ain't that scary, right? So what if we take the blue equation and times everything by 4? Well, if we do that, we end up with -32 equals -4a plus 8b. And if I take that and the green equation and I subtract them from each other, then I know I will get rid of one of my variables. That's why it's called elimination, because we eliminate one of the variables. So I'm rewriting the green equation underneath it. I've got everything all nice and lined up. So now it's time to subtract. And why am I choosing to subtract? Because 8b plus 8b does not make 0b's, right? Right? So I need to subtract and get 0b's is what's going to happen here. So the danger here, guys, gals, non-binary pals, is you're going to forget what we're doing as we move along. So I usually circle that. We're doing -32 minus 44. So that's going to be a -76. I'll scoot this up. Go. -4a minus 15a is -19a. A lot of people see that positive and they start adding them. So be careful. Focus on what you're doing. Remember, we wanted to subtract. That way this goes away, and it will. We're eliminating a variable. That's why we call it elimination. 8b minus 8b is 0b's, otherwise known as 0, right? Because 0 times anything is 0. 0b is 0. So now we get this, and then we divide by 19 to both sides, and we're going to get a positive answer for a. It's whatever 76 divided by 19 is. Well, if 19 were to go nicely into 76, 19 is about 20. 4 times 20 is 80. So 4 times 19 is 40 plus 36. Oh my God, it does go in nicely, doesn't it? 4 times 19 is 40 plus 36, 76. So A is just 4. Hooray. So if A is 4, pick an equation, sub 4 in 4, and then we get B. I'm actually going to go to this one right here. I'm going to plug in 4 for A. And I'll get B. So let's draw a line over here. -8 equals negative version of whatever A is, and that's what we're plugging in, so I'm leaving a space, plus 2 times B. And we know A is 4. So I've got -8 equals -4 plus 2B. Well, if we just turn our brains on for a second, right, what number do I add to -4 to get -8? Well, -4. So 2b has to be -4. Again, think about it. -8 is what I want. I've got -4. What do I add to that to get to -8? Well, this needs to be -4. -4 minus 4 is 8, right? -8. So I know what's under here has to be -4. That's the logic I teach my algebra students. If you're more comfortable just adding 4 to both sides and getting this, you do you. I divide by 2, or think to myself, what number times 2 gets me -4? -2, right? Again, I try to make my kids think as they're doing this stuff. Is it the most efficient all the time? No, thinking isn't the most efficient, but it is the point, I think. Thank you. So 4 and -2, which you enjoy, right? Those are nice numbers. Hooray. Dead giveaway on the next one, even if we're not going to do it. Describe all solutions is screaming that there is either going to be no solutions or infinite solutions. Remember, these equations represent lines. So pretend we have a blue equation that looks like this, and we have a green equation that looks like, well, I'll hold off on that for a second, actually. Remember what these lines represent. It's a collection of all the x's and y's, right? This coordinate right here might be like 3, 4, and this one might be like, I don't know, 2, -3, right? All of these dots, and all the ones I didn't draw in, because there are infinitely many dots on this line, represent all the possible values that make that equation true. So if I were to plug in any of these numbers to, let's say, this equation, it should come out true and equal -5. Now, I just made those up, so it's probably not going to work out. But that's what a line represents. It's all these dots, and there's so many of them. There's infinitely many of them that we just connect them into a line because you can't physically draw all of them, right? So here are all the solutions to my top equation, let's say, right? That's what this line represents. What if we have another equation, right? If I have another equation, let's say it's this line. It has a bunch of different dots on it that represent solutions to it. So maybe this is our bottom equation, right? All these dots represent solutions to that bottom equation, x and y pairs, right? Maybe like 1, 5 or something is on here, and that makes this true, and 0, 12, or whatever, right? So when we have this little squiggle here, it's telling you that I want the solution that works for both. Well, if you look at this graphically, there's only one solution that works for both. It's whatever this dot is right there, right? So we can have a situation where we have one solution, and that's what happened on the last few pages, right? We got like -2, what was it on the last page? -2 and 4 was a solution that worked for both the top and the bottom equation. We got 13 and 8/7 that works for the top and the bottom. With just a single equation, there are infinite solutions. But with 2, there might be one that only works for both of them. Another scenario you might have is that we have a blue equation, right? Here it is. And then we have a green equation. And they're parallel, meaning that they have the same slope. Or more importantly, meaning that the solutions that work for the green equation, all these dots, right? All these x, y pairs, all these coordinates. And all the solutions that work for the blue equation, all these x, y pairs, they don't have one that they both share, right? There's no shared solution here. So in this case, we would have no solution. There's no number or pair of numbers that works for both equations. Like if I plugged in 3 and 7 here, and I plugged in 3 and 7 here, they wouldn't come out equal. In fact, there's no combination that when I plug it in for one, also works for the other. That's another possible scenario. The only other scenario, if you think of these as lines, that we could have is that we have two equations, a blue equation with all of its solutions, right? And we have a green equation. And this green equation is literally the same equation as the blue equation, meaning that all of its dots that work for it are the exact same dots that work for the blue one. So instead of having one solution, only one spot where they agree, in this scenario, we have infinite solutions because every single one that works for the top will also work for the bottom. So if you think about this, it means in this scenario that both equations are literally the same equation. Here, both equations are the same except they're, well, let me say this. Both equations have the same slope. They're not exactly the same, otherwise they'd be this, right? It's like the same line, but just separated by a bit. Whereas these are exactly the same line in the same location in space. Or we have this scenario where we have two completely different equations and they'll intersect at some point. So when we're doing this, you should ask yourself, are these the same equation? Because if they're literally the same, guess what? They have infinite solutions. So let's look at it. 3x, 12x. Okay, I see a relationship there. 4y, 16y. I see a relationship there. 5 and 20, I see a relationship there. And they all have the same relationship, don't they? It's times 4. So if I take this top equation and times everything by 4, very quickly I think you'll realize that these are the same equation, or at least they look to be. So if I take this equation here and times it by 4, I get 12x plus 16y equals -20. So look at this green equation here. Right now, it doesn't look like they're exactly the same, but think about it. If I were to move the 16 over, I would subtract it. And if I had the negative 20 there, it would match, and the 12x matches as well. So that green equation, when I make it look exactly like this one, I get 12x minus 16y equals negative 20. Oh, so close. They're not the same, meaning it's not this, right? They're not. The question is, are they just two different equations that sort of look similar? Or are they similar enough where they'll be parallel and have no solution? Well, think about slope. You know slope is easy to identify when we have it looking like this, right? Y equals mx plus b. So let's turn our blue equation into y equals mx plus b. And let's do it in our heads. When I try to get y on its own, what am I going to do? I'm going to subtract 12x, right? I'm going to divide by 16. So that means I'm going to get subtract 12x and divide everything by 16. There's my slope. Again, subtracting 12x, dividing everything by 16. See how y is on its own? That's all y equals mx plus b is. Y on its own. I know, boring. If I do to the bottom equation, I subtract 12x. And I get y on its own by dividing by negative 16. What do I get? I get y equals 12 over 16x plus 20 over 16. Let's compare these two equations. This one and this one. Are they literally the same equation? No. Do they have the same slope? Almost, but not quite. Turns out they're the same equation, except this one's going down and that one's going up. So they're two random equations. They'll have one solution. What solution will they have? Where do they both intersect? I don't know. Don't care. So there'll be one solution. Doesn't say to find it. Just says describe it. So you don't need to do all this work, right? I kind of was explaining the concept and all that. You could just be like, ooh, they look similar. Are they the same? Turns out no. Turns out no. Let's look at the bottom. Using our same logic, part B. First off, let's make this look kind of nice. I can multiply it through and get 8 to everything and get rid of all this. And what do we get? 8 divided by 4 is 2. 2 times 3 is 6. 6x. That divides out. We get 5y. That multiplies 24. Looking similar, right? Are they the same equation? Well, if I rearrange this one and put the 5y first and the 6x next, I think it becomes obvious. These are the same equation. So if they're the same equation, where do they intersect? Constantly, right? They're the same line, so they're going to intersect constantly. Yeah, that's the same. That means we have infinite solutions here. So again, you don't need to spend that much time on these. They're not like a lot of work. You just have to understand the concept. If they're the same line, they're going to constantly intersect, which means they have infinite things in common, infinite solutions. If they're completely different lines, even though they look really similar, then they'll have one solution. If they have the same slope, then they'll be parallel, which they will have no solution. They will never intersect. Ladies, we've been going for about an hour now. Are we hanging in there? Okay. How do we feel about this concept? For real? Yeah. Really? Yeah. Okay. I do a lot of talking, and I'm like, there's no way any of this is landing, so it's good to hear that it is. Zoe was looking at this one the other day. Read the directions. For what value of the constant a does the system of equations below have infinitely many solutions? Well, you know if it has infinitely many solutions, it means both equations are literally the same, right? So what does a need to be so these equations are literally the same? Well, I noticed very quickly that, like, to get the x's to match, because again, if they are the same, there should be a way to get a match. I would times this by 3. So if I times everything by 3, I get 20. I should probably write this in a different color. 27x. I know, what an idiot. minus 6y equals negative 15. And if I rearrange this one on the bottom here, I get 27x minus 6y equals negative 13 plus a. So if these are going to be the same equation, have infinitely many solutions, what does a need to be so they match? Well, it looks like these already do, right? So a just needs to be a number so that this actually is negative 15. So what does a need to be so that this is negative 15 and they match? Negative 13 minus what gets you 15? Yeah, so it's got to be negative 2, right? This is an intermediate problem. Sometimes I do that. And again, there are lots of ways of doing these. That's probably the most efficient way. Other ways might take the whole page. How do we feel about these word problems? Some of Eric and Bob's weight, 6 green balls, 5 red balls. Janice noticing something with the clock and laughing to herself. Janice? Yeah, she's looking at her digital watch, and then she notices later, isn't it funny? She's a dork. I do. I had a lady that I used to go visit for Thanksgiving. Am I still there? Yes, I'm. Stay in the. Because nobody else is there. But I want it open just in case they do show up. Yeah, there's a lady named Janice and her husband Alfred. And I know, isn't that great? And no, but Alfred smoked a lot, and Janice did too, because it was back in that day. And they were next door neighbors to us when we first moved up north, because I'm from like East St. Louis area, right? And so they were really, really kind. We lived in a trailer park with them, and they would like babysit me all the time and take care of me when my mom was doing stuff with like my younger sister who was really sick, or my dad was coaching. And their sons and daughters are all in the school system that my dad worked at. And so we'd head over there all the time and hang out with them. And they were like grandparents to me, essentially. And Alfred died like maybe like 15 years ago, lung cancer, go figure. And then Janice was starting to develop Alzheimer's. And so she ended up moving with her son, Lance, who was a USC quarterback star, Trojans, right, out in California. And so she moved out to California with him so he could take care of her. Yeah. And she had like a southern accent. Lance, get in here. Get in here. The football game's on. Lance. And then they had a cat named Frisky. And Alfred had this like really low, because he's a bigger guy, really low voice. We go visit him for Halloween every year, even after we moved. I love them. They're great. Maybe. I don't know. I've never met an American named Alfred. But I think it's a great name, and it should make a comeback. Do we want to do any of these problems? Yes, no, maybe so? Well, sure, right? Like, yeah. Zoe and I looked at this one yesterday. So, Zoe, we did look at it. Olivia, what do you think? Like, the secret is that everybody's going to want to see these. Right? Like, if this is a video for everyone. So don't feel bad. When in doubt, we can just do them. All right. At a certain time, Janice notices that her digital watch reads 8 minutes after 2 o'clock. 18 minutes later, it reads B minutes after 3 o'clock. She is amused to note that A is 8 times B. Okay, write that down right there. A is B times 8. Right? B and A are not the same number, but if you times B by 8, you will get A. So this is a statement of equality. What time was it when she looked at her watch for the second time? Let's see if I can do this live. I haven't had to do this one in a while. At a certain time, she knows her digital watch reads 8 minutes after 2 o'clock. Cool. 18 minutes later, it is B minutes after 3 o'clock. She's amused to note that A is 8 times B. What time is it she looked at her watch second time? So I know that 2 o'clock, if we just have 12 be like 12 o'clock be 0, right? We think like international time here. 2 o'clock means 120 minutes have passed. And then we have like 120 plus A is like the current time. Does that make sense? Like 2 hours and A minutes after. And then I also know that like when she looks at her clock later, it's 3 o'clock. So it's like 180 plus B is her new time. So maybe I can make an equation here. So these two are not the same. 120 plus A and 180 plus B. They're different times, right? One's at 2 o'clock and change, one's at 3 o'clock and change. But when will they be equal? Well, if you notice, he looks at the clock 18 minutes later. So this is the time at 2 o'clock that she looks at it. If I were to add 18 to that, that's now when she's looking at the clock here, right? So in other words, I know that 120 plus A, if you add 18 to it, you'll get 180 plus B. 2 o'clock and change, add 18, now it's 3 o'clock and whatever, I don't know. And I also know A equals 8 times B. So guess what? I have a linear system, right? If I only had one equation, there are infinite answers, right? Think about it. 8 times anything gets me A, right? B could be 2, 4, 6, 8, right? It'll get me lots of different answers that I could make an equation for here. But if I have two different equations, I can solve for A slash B and win. Now, what's nice is substitution here, right? See how A is already on its own? What if I just plug 8B in for A? Okay. If I know A is the same thing as 8B, now I have one equation, right, where I can get B on its own and win. I subtract 120 from both sides. I get 60. 60 minus 18. 60 minus 10 is 50. Minus 8 again is 42. And I'll subtract a B. 7B. So again, I just got all my regular numbers together. I subtracted these two numbers from 180. I got 42. That's 60. Minus 10 is 50. Minus 8 is 42. Then I subtracted B from both sides. So B has to be 6. So we're asking, what time was it she looked at her watch a second time? Well, it's B minutes after 3 o'clock, right? So 3:06 is when she looked at it. So again, it's just trying to come up with some equations, right? What are we saying? How can we put it into math, right? We know that, where does it say that? She's amused to note that A is 8 times B. Okay, cool. Awesome. Write that down. We also know that this is our current time, that's our later time, and they're 18 minutes apart. So if I add 18, they will be the same time. Go to town, right? That's the idea. And again, I feel okay asking these complex word problems because, again, I tip my pitches, right? You guys have the same word problem every single week. The numbers just change. And so if you know how to solve it once, you should be able to get through it anytime, right? Doesn't matter what the numbers change. I like Janice too. So A was 8 times B. So for fun, that means A was 48. So she looked at the clock at 2:48 and then looked again at 3:06. Alrighty. Green ball, red ball, Eric and Bob. Yes, no, maybe so? Eric and Bob. Is that, I have an Uncle Eric, and that's why you said Eric and Bob, or Eric and Bob because you want to do Eric and Bob, the problem? So okay, the sum of Eric and Bob's weight. Well, E stands for Eric's weight, B stands for Bob's weight. Let's do that. Is, whenever you see is, think equal sign, is 9 times the difference of their weight. So it's 9 times however far they are apart. Now, spoilers, Eric weighs less than Bob, so I'm going to do B minus E. That way it stays positive. Okay? Because Bob weighs more, Eric weighs less. It also says the positive difference of their weights. Again, the positive difference would be B minus E. Negative difference would be E minus B, because Eric weighs less. Is 408 pounds less than the sum. So it's whatever they are added together, minus 408. Find Bob's weight. So our job is to find out what B equals. Okay. Well, first off, I noticed that there's 2 B's. There's a B. And if I literally just subtract those, now I get an equation with E in it, and I get E for free, don't I? Let's do that. If I subtract B from both sides, I get negative E equals E minus 408. So if I subtract E, I get negative 2E equals negative 408, which means Eric is going to be a positive 204. And if that's true, I can use that to find Bob's, right? Hooray. Yes, this is a linear system, but it's kind of like that one problem we did earlier where we got X for free, right? If you play around with it for a little bit, you might actually get one of the variables for free. And we did. So if Eric is 204, then I can just take that and plug it into this equation. So Eric is 204. And I'll do that in black. I should have done it in blue, but that's okay. Plus Bob will equal 9 times whatever B minus E is. Oh, and we know what E is. Scratch that out. E is 204. Cool. So it looks to me like we got 204 plus B equals 9B minus 9 times 204. Well, 9 times 200 is 1800, and 9 times 4 is 36, so it's 1836, which was a good year. If we add 1836 to this, ooh, that actually works out nicely. 1836. If I add 200 to it, I get 2036. If I add 4 to it, I get 2040, which will be another great year, I'm sure. If I subtract B, I get 8B. And so if I divide 2040 by 8, I get Bob's weight. Is 2040 divisible by 8? I don't know, but I know it's divisible by 2, so I could rewrite that as 1020 over 4. And now I know this is divisible by 4, because 1,000 divided by 4 is 250, and 20 divided by 4 is 5, so this is going to be 255. And that's Bob's weight. I think important to note in this one is, do you see how I logicked my way through this if it's divisible by 8? I don't know, but I know I can divide both by 2, right? And then after that, I realized, oh, 250 times 4 gets me 1,000. 5 times 4 gets me 20. So 250 plus 5 is my... How are we feeling? Yeah, but at least they end in zeros. And remember, I can be your calculator. Because one of the benefits of having me as a calculator versus your calculator is I can tell you, Zoe, no, you don't need to do any of this. Stop, please stop. Your calculator won't tell you that. It'll just keep telling you answers. Cool. All right, so 544. Green ball, red ball, yes, no, maybe so? Oh no, do you need another one? Please stop. Okay. No, it's okay. I can skip over it. Skip. Yes? Okay. Don't have to. 552. I believe that's an area code that I used to live in. I did. Yep, that's right. Me and Elon Musk. Hate that guy. All right. Area of a square equals the square of a length of... So just so you know, all of this is just telling you like some stuff just in case you didn't know. The area is the length of the side times each other, right? The perimeter is just the sum of all four sides, right? That's how perimeter and area works for squares. Good. You don't need any of that. That's just telling you how perimeter and area work. You understand this, right? Good. Wonderful. Excellent. The sum of the areas of two squares is 205. So think of it. If I have a square and I find the area, I take the side lengths times themselves, right? Let's say the side length is x by x. Well, that means the area is x squared, isn't it? So one of my squares has an area of x squared, and the other one has a different area. Let's call that y squared. The sum of their areas is 205. So that's one square, right? Whatever its side length is squared, that's its area. That's the other square, whatever its side length is squared. If you add those together, apparently you get 205. Well, the difference in their areas, and it doesn't tell us which one's bigger, so we'll just assume x is bigger, the x square, gets 133. It's a linear system, right? And it might not look linear because you're like, wait a minute, squares. It's a quadratic. Yes, but we can treat it the same. I think we should do elimination for this one. You know why? They're already opposites. So what if we just add them? Add them. Again, if I have my soundboard. If I add them, I get 2x squared, right? X squared doubled. When you add something to itself, it doubles, right? 2x squared. And then y squared plus negative y squared is going to be nothing, which is why we did it, right? So that goes away. And then we get these ones added together. So it looks to me like 338. And that's divisible by 2. 300 divided by 2 is 150. 30 divided by 2 is 15, so I'm up to 165. 8 divided by 2 is 4, so 169. Now, if you don't know already, and if you didn't, it would be okay. You could say x is going to be equal to the root of 169. Now, you know that from working with quadratics that we have two answers, right? One positive and one negative. But think about the context of the problem. Is our square going to have a negative side length? No. And that's what x stands for, right? The side of the square. So it's only going to be the positive version. Now, maybe you also did not know that the root of 169 is a nice number. But you do now. You'll memorize this one. 13 squared is 169. Nice. So we know 13 is 169 squared, so we know the 169 rooted is 13. Now, imagine you didn't know that. Could you just circle root of 169? Oh, for sure, bud. For sure. For sure. So 1 square, the bigger square apparently, has a side length of 13. We need to find the side length of the other one because we need to find the sum of their perimeters. So we're going to add up 13 times 4, right? And add up whatever times 4, and that's going to be the sum of their perimeters. So we need to find out what y is. Well, if I know that 13 squared is 169, then when I plug that in here, I'm going to get 169 minus y squared equals 133. So I'm actually going to subtract 133 from this and get 36, and I'm going to add y squared to the other side to get this, which means y has to be 6, or the root of 36. Again, in this case, it comes out nicely. So if one of my squares has a side length of 13, what's the perimeter of the x square then? What's the perimeter if the side length is 13? It's times 4, right? Perimeter, right? Add up all the sides. So 13 plus 13 plus 13 plus 13, otherwise known as 13 times 4. 40 and 12 makes 52. What's the perimeter of the y square? 6 times 4, right? And then the total perimeter, again, I'm just making up variables here. P sub t, sub x, p sub y, they're all perimeters. Total perimeter is just going to be 76. That's what they wanted you to find. How do we feel about the logic here, right? I've got an unknown square, so it has some unknown side length. The area will be unknown squared, right? The other one has a side length of y, so its area is y squared. Here's the sum, there's the difference. Elimination seems to be a good way to do this problem, but you do you. Only going to get positive answers because these are squares. They don't have negative side lengths. Yada, yada, yada. And now for the moment you've all been waiting for. 561, which turns out does not have a very nice solution, but we know how to deal with something that's not a nice solution. We know how to deal with that. Yesterday? Yes, except this one is a different version, right? Because I made it for the quiz yesterday. And this one does not come out to a nice solution. The good news is that there's one right after this that's literally the same thing, right here, that does come out nicely. Again, I did it last night because I was like, oh no, Zoe came up with a weird answer in 561. Was it Zoe or was it me? And it was me on this one. But again, we know how to deal with when it's not a nice answer, right? You just like get all the variables out and circle it. But so let's take a look at this. Before you start solving anything, the whole thing you should be thinking is, can I make this problem easier? What do you notice about these three equations, or at least one of them in particular? X is already by itself. That's great. So we get X on its own, and boom, we're off to town. What else do you notice? They are. That's good. So we probably don't need to multiply to get rid of anything. Ooh, if you did elimination, right? Those z's would go away. That could be really nice. Using any method. So if you want to do elimination, that could be nice. Another thing is that all these are even. So if you wanted to, you could divide all those out by 2. If you're going to do like substitution and get z on its own easy. I don't know. So we got options. But I think your idea, which I didn't even see originally, is we should take these two equations. Let's do blue. Let's do green, and let's do orange. If we take the orange equation and add it to the blue equation, we'll get rid of one of our variables, right? Now, that doesn't mean you should do this every single time for this problem. For those of you just tuning into my class for the first time ever, this is not, here's how you do the problem, because unfortunately, at higher level math, there is no one right way to do it. There are lots of ways, and some ways are more efficient. So in this case, it looks like this could be pretty efficient, right? These both, we add them together, and we'll get rid of one of our variables. So that could be nice. Orange and blue, if I put those together, and I'll just write them out so we don't make a mistake, equals -5. And then 6x plus 4y minus 2z equals 6. I want to add them, because when I do that, one of my variables will go away. I'll get 3x, 5y's, no z's, which was the whole point, and then +1. Cool. So think about what we did here in the context of substitution, not elimination. I just took these two equations, the orange and the blue, and I used them, right? So I don't want to do that again. Let's pick a different combo here. Maybe what we could do is we could do elimination with the orange and the green. I don't want to times this one by 3 because then that's going to be 30. I'd rather multiply this one. So what if I times this one by 3, the orange equation, so I get the y's to match up? And then that way I'm not making gigantic numbers like 30. I only have 15. So I'm going to take the orange and the green now. And I'm going to times the top one by 3 and get -9x plus 3y plus 6z equals -15. And I'm going to combine that with elimination with my green equation. Again, notice how I'm not using the same two equations twice, right? And if I do that, do I want to add or subtract to get those y's to go away? Add them, right? 3y minus 3y, right? We just want to keep the signs, essentially, so we're going to add. So we're going to get -8x when I add those. That becomes nothing. That's the whole idea. Again, double check. 3y plus -3y is 0y. That's why we did it. And then we get 11z. If I add those, I get -5. So now I've got two equations here and here that have just two variables in them. This is great news, because now we've turned this problem here into a problem we already understand. Here's our new linear system. And I'll use, let's do purple and different color green, maybe? I think it's good. So let's call this the purple equation. -8x plus 11z equals -5. And let's call this the green equation. 3x, by green I mean dark green, 5y equals 1. And here's our new linear system. So just like that, we've turned this problem into a problem you already know how to solve. We've done systems like this before, right? Get one variable on its own, substitute, right? I've got bad news. You see how this one has x and z and that one has x and y? Bum, bum, bum. Is that going to be a problem? It definitely will be. We have two equations with 3 different variables. I'm going to solve that. That's kind of annoying. Sometimes this happens when you're going down rabbit trails that you haven't gone down before. But one of the reasons I go down them is because you might go down them. What do? Yeah, just go. You can go. So one of the reasons I go down these rabbit trails and make these mistakes is because you might go down them as well. And then the question is, what do I do? How do I identify when I'm going down a dead end? Do you see how we have 2 equations with 3 variables? That's not going to work. We need at least 3 equations if we're going to have 3 variables to solve it. And so we wish we didn't get rid of that y. We wish we actually got rid of the z. That would have been nice. Let's go back over here and try that again. This isn't going to be very useful. This isn't going to be very useful. So if I wanted to get rid of the z using these 2 equations, maybe times the top by 5, right? And then subtract. Let's do that. Orange equation going to get negative 15x plus 5y plus 10z equals negative 25. And I hope you understand why this wasn't helpful, right? Again, we ended up with two equations with three different variables. We're not going to be able to do anything with that. And then for the light green equation, we're just going to leave it the same because now we can... oh, no. We're looking at the green equation. I'm going to double everything here to get those 10s to match. So 2x, because we want z to go away to match this one. Negative 6y plus 10z, 20. And now in this scenario, Zoe, we're going to add or subtract to get those z's. Very good. Don't forget we're subtracting everything. Negative 15x minus 2x is negative 17x. 5y minus negative 6y. That's a double negative, so we're really just adding there. That's 11y. 10z minus 10z is nothing. That's why we did it. And negative 25 minus 20 is negative 45. So now we've got a purple equation that'll actually help us out. Negative 17x plus 11y equals negative 45. So there's our system. And this will be helpful because it's two variables, two equations. And we'll be able to get one on its own by doing substitution. So, x or y on its own. What do you want to do? Because I don't want to do elimination here, right? Getting these to match up by timesing is just going to be nasty. X. Okay, top equation, bottom equation. Green or purple? Bottom? Okay, so let's get x on its own. That's super easy. I just subtract 11y, and I divide by negative 17. Now, you'll notice that these are all negative, so I can just make them all positive now by dividing out that negative. So x is just this. We have diverged. You can try and solve it on your own from that perspective if you want. Okay, so now we get this. And again, one of the reasons I like doing this one is because all those negatives are going to divide out. So I just times everything over here by negative 1 in top and bottom. And when you do that, that's like timesing by 1, so it doesn't change anything. So I can just leave this side the same while changing that side. So I now know that's what x is, so I'm going to plug it into my dark purple or dark green equation. For x, 3 times something plus 5y should get us a 1. And if I plug in 11y, and like I said, this one's going to come out nasty. All over 17. First off, I check. Can I do 3 divided by 17 and simplify that? Nope, I can't. Does 17 divide either of these? No, it does not. So it looks like I'm going to have to distribute the 3 and times everything by 17. Not fun, but sometimes that's just the breaks, kid. So we get 33y plus 120 plus 15 is 135. I'm going to times everything by 17 now. Again, this just eliminates that divides by 17. If I times 5 by 17, I get 50 and 35, which is 85. And 17 times 1 is 17. But now we've got an equation with y, and we can actually solve. So 33 and 85. Oh, well, that's 88. 88 plus 30 is going to be 118. And if I subtract 35, I'll subtract 17 first. I get to 0. That's going to give me 118. Negative 118. Oh, my God. Is y going to be negative 1? Does this come out nicely? Did I just do this wrong last night while I was taking care of Abigail? Could have been. Could have been. Kind of a busy guy. Oh my God, this might come out nicely. You what? No, but it's funny you mentioned that. Did you know that not always I literally change the problem? I just like double everything so it's the same thing. It just looks different. I did that on the next one. All the answers are next. Yep. I know. So if y is negative 1, I can plug it in there and get x. So while you're gone, Olivia, we realized that this method wasn't going to work because we had 2 equations with 3 different variables, right? So instead of eliminating y over here, we eliminated z. So I did the same thing, but this time I got z gone. And that way we could do get x on its own here. and then plug it into the green one. Okay. And so we got y equals -1. So now I can go over here and get what x is. So that's good. So x is going to equal whatever 11 times whatever y is, plus 45 divided by 17. And guess what? If x is, or y is -1, that's -11. -11 plus 45 is the same thing as 45 minus 11. That's going to give me 34. So I have 34 over 17, and guess what? That means x is 2. Maybe z is just really nasty, and I solved for z first last time. That could have been. I often solve. I suppose so. It also looks the most like my x's, because like my x if you turn it on the side. So that's why I try to get rid of it. The key to drawing a good z is you have to make sure that the middle part is small. Because if the middle part's big, let's do that, then it can look like a sideways x. That's cute. I try to think back, and a lot of my writing has changed because I've become a math teacher. But like, why do you write things the way you do? It's because you probably saw your teacher write on the board and you thought, I want to write. Like, I think that's why. Is it Zoe or is it you that does your A's like this? That. Oh god, I just did a 2, which I cannot do anymore because. Oh god, how did I do that? That was so perfect. Okay, someone does that. Someone does their A's like this, and that was like the most perfect A I've ever done. Like that. Holy crap, that looks amazing. Very fancy looking. I probably need to avoid that because the same reason I don't write my 2's like this anymore is because I've said this before. Lowercase delta is that, and they look really similar. Like if that goes just a little further, so I make my 2's like that. Yep, and that's what I did too because my teacher used to do that. But like then it looked like delta, and I taught an entire class with calculus where they thought I was drawing the number 2, and I was like, oh no. And then I made my 2's like this, and that made my z's look bad, and so I had to add the line, yada yada yada. That's cool. Very dad thing to do, I feel like. I write in all caps occasionally. I prefer cursive. Nobody knows how to read cursive. Whenever I do cursive on the board, it ends up because it's way faster to write that way. Writing in print quickly is what gets me in trouble. We know x and y. Now let's go get z. I don't have any nice equations with z in it, so I'm just going to take these two and plug them into whichever one I think would be most fun to deal with. And I think the answer for me would be the middle one. So if x minus 3 times whatever y is plus 5z equals 10. All right, Zoe's back. Stop talking about it. Awkward. So I know x is 2. X goes here. I know y is -1. -1 goes there. Again, we plug in parentheses, especially for occasions like this, right? That's going to come out to a positive 3. 2 plus 3 plus 5 times something equals 10. Well, guess what? Z should be 1. 5 plus how many 5s equals 10? Well, 1 5. Ta-da! Z is 1. Has to be. 5 plus how many 5s is 10? 5. So this one did come out nicely. Yay! I have to feel less bad. There's only one problem so far that didn't come out nicely. Ugh. Joseph, how are you? That is your full legal name, right? Your government name. All right, next one. Sorry. This one's a lot. It's just bigger than all the others. I know. Yep. Next year I might change some of these to more advanced. Your algebra skills are less than I think every single year. I have to change this quiz so many times. No, like the school in general. Like last year I had even more that were like I have to change it every year and change my expectations. Hopefully over time we'll get better, and then I'll be able to actually have these be intermediate. But yeah, for a lot of you guys, started. All right. You might notice elimination right away. Those z's will go away. Now the danger of that is when you pick your other two, we learned last time we have to get our z's to go away there too, right? So you can do that, or you can do substitution, and you never have to worry about any of that. What do you want to do? Do you want to do elimination like we did last time? Okay. So let's do orange equation, green equation, light green, and let's do dark blue. So orange and green, if we add them, z will go away. Negative 3x plus 5y minus 2z. And you got to remember, like, while it takes a long time to get through these, it's not because the math takes that long, although it does take a little while. It's because I'm having to explain everything and kind of like pause and all that stuff. And remember, the idea is that you're not doing all of these at once. It's that you're doing them over the course of a semester. But Lord knows we don't do that, do we? Yep. It's okay. First semester is always like this. Then second semester you figure it out, and you're like, why was that last semester so hard? And it's because you just didn't take it seriously until it was too late. All right. So anyway, here we go. And by too late, I mean just until it was too late to make it easy. Now you have to do a lot. So if I add these, I get negative 11x, 7y, nothing, which was the whole point, and 8. So now let's see, let's do, eliminate z. Let's do blue and green. I don't know, I'm just feeling like it. No, let's do orange and blue, because there's an 8 there. 8s are big, I don't want 8s. So let's do orange and blue. And I want the z's to be gone. So I'm going to have to times everything by 3 in the top. The heat. Yes, please. Move it to the cold side. That's all you need to know. It says like cool or warm or something. Move it to cool. Or like move it not as far to the warm. This will mostly affect me. That's okay. It might not even be on right now. Sorry. Well, no, but wait, it's not working. No. No. It's that on the weekend, it probably isn't even on. This is just how hot it is in here. Sorry, this thing produces a lot of heat. You want to open a window? Oh, I thought you were... Oh, okay. I thought... Okay, yeah, move to the hot side. I get it. No. Because then she's like, they're trying to freeze this out. And I was like, oh, no. I thought you had different opinions. Okay, got it. You're both too warm. Okay. All right. All right. I'll have to go back to the video and see what you said, because I swear to God you said you were too warm. I know you did not say thermostat, so now you're just making stuff up. There's no way you said thermostat. Well, I have a recording and we'll find out. All right, so now I'm going to take the blue equation and I'm going to times everything by 2. And I get negative 2x plus 6y plus 6z equals negative 20. And when I eliminate with those, I'm going to want to add them, because that'll actually make the 6's go away. So I get negative 11x's. I get 21y's. I get no z's, because that's the whole point. Negative 6z plus 6z is 0. And I get negative 20. No common factors here to divide out. No common factors here to divide out. So those are as simple as I can get them. And now, glory hallelujah, we have 2 equations with 2 variables. And now this is a problem we know how to solve. And if you notice, one of our variables matches the other. It's coefficient, right? So we could do elimination again if we wanted to and eliminate the x's. Now, guys, gals, non-binary pals, do we want to add or subtract those negative 11s to make them go away? If we add them, we get negative 11x plus negative 11x's. That's going to be negative 22x's. We got to subtract them. And here's why. The double negative makes them add. Now, the way I think about it, just quickly in my head, anything minus itself is 0. So negative 11 minus itself will be 0, right? Or negative 11 plus 11, right? We'll get you 0. So that goes away. And we get 21 minus 7, which is 14y. Don't lose your y's. And then we get negative 28. which means y has to be negative 2. Olivia knows this. Because if y is negative 2, then we can plug it into either of these. I'll plug it in this one. And we can get x. Negative 11x is plus 7 times whatever y is equals 8. We know y is negative 2. The negative 11x's minus 14 equals 8. That means the negative 11x's equals, when we add 14 to this side, 22, which means x is negative 2. And if x, oh god, if x is negative 2 and y is negative 2, I can plug both those in and find z. So I'm going to take this blue equation at the bottom here, because you're going to be able to see it right here. I'm going to plug in x and y. So be careful when you do this. Negative of whatever x is plus 3 times whatever y is plus 3z will equal negative 10. I know x is negative 2 and it goes here. I know y is negative 2 and it goes here. Double negative. So I know, and I screwed this up last night multiple times. 2 minus 6 is negative 4. If I add 4 to this side, I get negative 6. Not negative 14, mister. Adding 4, which means z has to be. All three are negative 2. I had fun with that one, apparently, when I made it. 3 or 4 weeks ago, probably. I was like, well, what if all the answers... It's okay. The whole point is not to write these down unless you're going to look at them later. And I guess you could during the quiz, right? The most important part is being here for the show, the experience, right? Because if you're writing down stuff and you don't know why you're writing it down, it doesn't do any good for you. We're now on the advanced. You want to see this one? You want to see how easy it is? So substitution is like, hey, I know x equals all this crap. So wherever I see an x, I can plug in all that crap, right? That's substitution, right? Check this out. I know this equals 333. And I know this equals 333. So these two things are equal, aren't they? See how this is equal to 333? Well, so is that. So guess what? That and that must be equal to each other. This is a substitution. You're replacing the 333 right there. Instead of replacing a variable, you're replacing a number. You're replacing this 333 with all of this. Because this is 333, right? So wherever I see a 333, I can replace it with 11p minus 97q. Are you following me on this? Because this is the big brain play. This is the whole point of this one. I know that this equals 333. So wherever I see a 333, I could replace it with that, right? Well, I'm going to replace this 333 with this. I know. And it's got a diamond next to it. Because, again, it's all about seeing that big brain play. So I'm going to add 98q to this side. And right now, this doesn't look very promising, right? We have one equation with two different variables. What's going to happen here? If I add 98, I get 1q on this side. If I subtract 11, I get negative 1p on this side. That means the negative version of p is the same thing as the regular version of q. This can be helpful. Because guess what? Wherever I see a q, I can replace it with a negative version of p. So I'm going to take that top equation. And I'm going to replace any q I see with negative p. So I've got 11p minus 97 times whatever q is equals 33, or 333. Well, I know that p is the same thing as, or q is the same thing as negative p. So I'm going to plug in negative p here. So now you'll notice I have one equation with one variable. We can actually get p on its own, right? So 11p plus 97p equals 333. So p, I have 108 of them. 108 p's equals 333. So p equals 333 over 108. Now we got to find q. Think about it. If p is this, q is just the opposite, right? The negative version of p is the same thing as the positive version of q. So the positive version of p is the same thing as the negative version of q. So Q is just going to equal the negative version of this. Negative 333 over 108. Again, slow-mo. Here's how P and Q are related. If I know P is this, then if I negate it, I get Q, right? Ta-da. How you feeling? Really?
Yeah.
For real? You understand the idea if P is this, then the negative version of P is Q? Yeah? Okay, good. Because there are a lot of words here, but that doesn't mean that it's landing and making you go, aha. Okay. Like that cookie? Like that cookie? Cookie in your sleeve? Quiet? In lunch? All right, this is basically saying, hey, how do you solve a system of equations? Like, don't even worry about the numbers. What would you do, right? So check it out. Right away, if I wanted to solve this, what do you notice? If I wanted to solve this for x and y, like let's pretend those a, b's, and c's are all numbers, right? What do you notice right away? Right, so they're different numbers here, right? But they're the same numbers there, which means we could do elimination, couldn't we? So if I eliminate these by subtraction, I get nothing here. I get by minus cy equals d minus e. Again, I can't like subtract those. Like normally it'd be like 10y minus 4y is 6y, but I don't have numbers there. So it's whatever this is minus that, right? Whatever this is minus that. And now you notice that the only variable we have here is y, because b, c, d, and e, while they're variables, aren't x and y, right? They're not the real variables here. A, b, c, and d are what we call parameters. They're similar to variables. They're basically variables, but again, we're trying to solve for y here. So if I try to solve for y, check this out. Check this out. If that were 10y minus 4y, you'd say we had 6y, right? So you would take whatever number's there, minus whatever number's there, and say you have that many y's, right? So guess how many y's we'll have? We'll have whatever this is, y's. So again, if that were a 10 and that were an 8, you would do 10 minus 8 and get 2, and you'd say we have 2 y's, right? But I don't know what those numbers are. But you can still do the same logic. Whatever this minus this is, that's how many y's you'll have. Also check. See if I were to distribute that y, we'd get back to this. Another way to think of this is that I factored out a y. They both had a y in common, so I factored out a y. This is just y times b minus c. And again, the idea is we want to solve for x and y here. So to get y on its own, I have something times y equals d minus e. Well, if I divide by this to both sides, then I know what y is. It's whatever this is. Y will be d minus e over b minus c from the original problem. And if you want me to plug in numbers, I can, and we can prove that this will be the case. But even without numbers, we can see that that's what it will be. And that's why we call this a proof. I mean, I could change out B, D, C, and E for F, G, H, and I. I could also make, instead of A and A matchup, I could make B and B matchup. But do you see the logic behind it? You need to be honest. Elimination gets me to here, and then I can just solve for y. Because the two things we want are x and y. So I'm going to solve for y by eliminating the x's. I know whatever this is minus this is will be how many y's I get. And if I had 10 y's here, you divide by 10, right? So divide by that. Whatever this is what y will be. Again, if you did geometry with me, you would have been doing more things like this. Actual, like, proofs. I know. But they're really not that bad. So I know it's a big shock getting to Algebra 2 and having to do all this stuff, but better late than never. That's what y will be. Now, if y is that, Like, let's say y was like 6. Wouldn't you go back in and plug 6 in for y and solve for x? Right? Let's get x on its own. So I just took the top equation. I'm going to get x on its own by doing this. And then dividing by a. That means x will equal d minus b times whatever y is all over a. And you would plug in this for y. Yay! X is whatever this is. Remember we talked about earlier how when you have a really nasty number, you just kind of leave it alone? A, B, C, and D, and E are all just numbers. So whatever this ends up being, that's what X will be. That's it. I just took the top equation, got A on its or X on its own, and plugged in what I found Y to be. We'll zoom out. This is what we call the general solution to the problem. There are no specific numbers here. It's just this is generally what will happen. You'll do this stuff. You'll get whatever that is. And now you can kind of see the relationship to what y is versus what you're given. And this will be what x is in relation to what you're given. In fact, these, you could call them formulas. Would I ever use them? Oh, God, no. Oh, God, no. You might. Is it okay if I move on to the next one? Okay. Remember, I'm doing these for you. Are we doing 551? This is what we call, it's the advanced box for reciprocal variables. So it should be like the second column, or sorry, the second row, last column. Or the last row, last column. I don't know. Want to see them? Okay, if you want to do them, we can. It's up to you. You don't remember, you don't need to get every single one right to get a good grade. For sure, yeah. Zoe, you had a method of doing this where you would like see the common denominators. I can do elimination. You can totally do that. Personally, what I would do is I would times everything by x, y. I'm just going to show real quick. So Zoe, if I times everything by x, y, x divides out the x, and I get negative 6y. Y divides out the y, I get negative 7x. This becomes negative 2xy. Same thing here. If I times by x, y, x's divide out, I get the y. Y's divide out, I get the x. And then this, none of those divide out. And then you could just solve this using regular methods. Down here, let cube root of r and root of s be like x and y, solve. And then we have the magic square problem that Zoe loves. Let's move on to quiz 2. Before we do that, we're going to take a quick break for me to use the restroom and you guys to rest your brains. But think about the ones you want to see. I'll be back. All right. Quiz 2. What are we looking at? Hopefully not the number line one. Hopefully not the plotting the points one. At least, if we're trying to be efficient here. Yeah. No. Since when? With what time, Zoe? I was here with you until like 5 o'clock. I went home. Abigail was sick. I went to bed at 6, and I woke up today. I couldn't stay awake. Yeah. Then I woke up when Abigail was really sick in the living room, and I helped her at midnight, and then I went to bed again, and I woke up at like 9:30. Oh, no. I looked at those individual problems because I knew that you were getting weird answers, but I didn't grade it.
Can we look at the first intermediate first?
Yep. All right, determine which of the following points is farthest from the origin. So this is a distance formula problem, which, good news, distance formula is just Pythagorean theorem. So let's say this is 0, 0, the origin, and this is your point. We want to know how far away they are. Well, good news. This is just a right triangle. And so if you know the sides of the right triangle, these two sides here, you can figure out the hypotenuse, otherwise known as the distance between your 2 points. So for instance, let's pick this point right here. 5, 1. That's the first one we have to investigate, right? So how far is it away from 0, 0? Well, we don't know how far it is here, because that's kind of a complex problem, but we do know how far it is away horizontally, right? How far are these apart horizontally, 0, 0, and 5, 1? 5, right? Because 0 to 5 in the x direction is how far we are apart horizontally. How far apart are they vertically? Not very far, right? In fact, my drawing is not to scale. This should be a very short blue side, shouldn't it? Right? Vertically, they're only 1 apart. So my triangle is going to look like this. At least it's going to have those numbers. It's not going to look like that. It's going to be very short on this side and very long on that side. And I can use Pythagorean theorem to figure out how far they are away. So all I did was take the horizontal distance. In the vertical distance, I square them, add them, root them, and I get c, because you know a squared plus b squared equals c squared. So a squared is 5 squared. B squared is 1 squared. And I should probably wrap these in parentheses because I'm plugging in for A, B, and C. Or at least A and B. And I know c squared is what I get from that. Now, we don't want c squared, right? We want the regular length here, not the number squared. So I'm going to root both sides, and that's going to get me c, this unknown length. So 5 squared is 25. 1 squared is 1. So it looks like I'm going to get, don't forget there's a root here, the root of 26. Okay? That's how far 5, 1 is away from the origin. It's root 26 away. That's all. What is root 26? Slightly bigger than 5. Right? So I'm going to write that down. This one is root 26 away. Now, if you're clever, you'll realize that only some of these are worth checking. 7, 1, we can do in our head. How far is negative 7 away from the origin? Well, it's 7 away, right? So 49. 1 is 1 away, so 1 squared. This is root 50. These are both 5 away, so imagine these are both 5s. We have 5 squared and 5 squared is 25. That's root 50 as well. 4 and 6. 16 when you square it, and 36. That's going to be root 52. So right now we have a winner, root 52. And 3 and 6 is going to be less than 4 and 6, so we don't even need to check that one. So it looks like 4, negative 6 is furthest away from the origin. How do we feel about that? For real? Because I feel like you guys might be writing stuff down and not really paying attention, and that's going to be a pain, because if you're writing stuff down and you don't know what it means, it's not going to be as useful as if you were just watching. We don't really do the show in my class as much as my other kids did, and usually by finals they figure that out. You guys are doing this for the first time. Does this make sense? Do you understand why I'm doing this? I can go from the top. How far is something away from the origin? Well, I can break it into a right triangle. 5 away, 1 away. Pythagorean theorem says a squared plus b squared equals c squared. C squared will be this side length squared. So I can find that. So I know 5 squared and 1 squared. If I add them and I root them, I'll get c, this side length. So it looks like root 26. I can do that all in my head. What's up? You have different numbers? Are we using different quizzes? Oh. What numbers do you have in the front? Okay, so I'm using an old version. That's okay. Allow me to run through it quick again. Uh-oh. Are you still there? I am. All right, so real quick in our heads, if you were to imagine the triangle that this makes with the origin, it's 3 by 10, right? So that means 3 squared is 9, 10 squared is 100. We add those together, we get 109, so this is the root of 109. That's how far it is away. That's 7 away and 8 away, so 49 and 64. If we add those together, 40 and 60 is 100. 9 and 4 is 13, so that's root 113, so it's further away from the origin than the last one. 81 and 25 is 106, so that's root 106, so that one's actually the least far away so far. 9 and 81 is root 90, so now we have a worst one further down than all the rest. 64 and 36, that's actually going to make root of 100, which is actually 10 on the dot. So which one's furthest away? Looks like this one. -7, -8. And again, I'm doing Pythagorean theorem in my head. I'm squaring them both. I'm adding them. I'm rooting them. That's how far something will be from the origin, because we drew that triangle earlier. 815, which is an area code I do live in currently. Recall that the root of x is the distance between x and 0 on the number line. Okay, let's recall that. Here's my number line. Here's 0. Here's some number x. How far is x away from 0? Well, if x was 10, it'd be 10 away, right? So it's whatever the amount is away. And the reason we have to use absolute value is because imagine x is negative. How far is it away? Well, if x is -10, it's still just 10, positive 10 away, because distance doesn't care about direction. So no matter where x is in relation to 0, how far is it away? It'll be the absolute value of x away, the positive distance away. So how does this relate to distance between x and y? Well, if I have x and y here on the number line, let's say it's like 10 and 17. If I subtract them, I find out how far they are apart, right? Distance is subtraction. If x were bigger than y, I would get a negative number, right? X minus y, get a negative number. And so the distance is just going to be how far they're apart, right? Distance is subtraction. And it's going to be the absolute value, because distance doesn't care what direction we're going in, right? If this one's 10 and that one's 17, this is 7 apart. If this one's 17 and that one's 10, even though we do 10 minus 17 according to this, it's still just 7 apart. So the two things I need you to talk about here are, 1, subtraction is distance. And 2, absolute value. I'd probably write this differently. Absolute value, because distance is directionless. In other words, distance does not care. Directionless. Distance doesn't care about direction, right? If I'm 10 feet away from Zoe, Zoe's not negative 10 feet away from me, right? So absolute value eliminates all negatives, because distance doesn't care about which one's bigger, which one's smaller. And subtraction tells you how far things are apart. That's all. Distance is subtraction. Absolute value doesn't care about, or direction doesn't care about, direction doesn't care about, distance doesn't care about direction. Absolute value. I wrote these horribly. First, I wrote them in cursive. second I wrote them in like reverse subject-object order. Ugh. So distance is subtraction. Distance is also directionless, which is why we have absolute value. Does that make sense, what I'm saying here? How far are two things apart? Well, they'll be this far apart. Subtract your two things, figure out how far they're apart, and then make sure you take the absolute value because remember, you can't have negative distance, positive. We need to see 8, 2, 3. You guys know how to graph the line x equals 3.5? Or y equals negative 10? That's okay. You guys know how to graph x equals 3.5? You know how? I've got good news for you. Now, normally we have like x equals 2y plus 7, right? And that's like all the numbers that have that relationship, right? Here it's saying I want all the points that have this relationship, where x is 3.5. So check this out. Where is x 3.5? This is the x-axis. So where is x 3.5? Well, x is 3.5 here. 1, 2, 3.5. But there are other coordinates that have 3.5 for x, aren't there? This coordinate is 3.5, 0. So it definitely does have 3.5 for x, right? This doesn't care what y is. It just says x has to be 3.5. What other coordinates have 3.5 for x? 3.5, comma 1. 3.5, comma 2, 3.5, comma 3, 3.5, comma 4, 3.5, comma negative 1, negative 2, negative 3. So very quickly, you're getting to see what this line is going to look like. What is it going to look like? Don't say a straight line. All lines are straight. It's a vertical line, right? So x equals 3.5 just means all the points where x is 3.5. And guess what? This is where all the points are 3.5. This line right here. So this is the line x equals 3.5. Now what about the line y equals negative 10? Well, same logic. Where are the coordinates where y is negative 10? Well, the first one I can think of is here, 0, negative 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 0, comma negative 10 is where y is negative 10. But there are other coordinates with negative 10 for y, right? 1, negative 10, 2, negative 10, 3, negative 10, 4, negative 10. We also have negative 1, negative 10, negative 2, negative 10, negative 3, negative 10, negative 4, negative 10. So guess what? This is going to be a horizontal line. Ooh, I need to do it. Drawn. And that's it. These lines are actually super easy to draw if you know what they mean. But if you just memorize stuff, you probably forget it by the time you reach calculus, which is why I love asking calculus kids how to graph lines like this. Because they never really actually learned it. They just kind of memorized it. And memory fades over time, whereas understanding grows. Which is why they have so much trouble in calculus drawing asymptotes. Don't ask me what an asymptote is. You'll learn something. So, how do you feel about that? All the points where x is 3.5. All the points where y is negative 10. Now we're going to talk about slope. What's the slope of this line? Well, if you notice, if we do slope formula, like between here and here, the y value changes, but the x values don't, right? All the x values are going to be 3.5. So it's going to be as much change as you want in y, no change in x. So it's going to be something over 0 for our slope, which is undefined. Down here, our slope is going to be, you just pick 2 points, right, between here and here. Looks like we're having some amount of change in x. But we don't have any change in y, right? We're not going up or down, so it's 0 change in y. So that's 0 over anything. And 0 over anything is just 0 slope. And that makes sense, because this is a flat line. It doesn't have any steepness. So this one has 0 slope. Whereas this one has undefined slope, because no change in the x direction, only a change in the y direction. 0 change in x, no change in y, undefined. How are we feeling? Undefined, 0. Turn the page. Let's look at 824 real quick. A lot of words here. Let's zoom in and let's talk about it. It says, first, tell me if the slope is positive, negative, 0, or undefined. Well, first off, this one's going up and to the right. This is a positive slope. We okay? Okay. So positive slope. Agreed? It's going up and to the right. If I were to go up and over, I'm going up and to the right. And so that's both positive directions. Positive divided by positive is positive. Now the question is the slope for this line, we'll call it M, greater than, less than, or equal to 0? Or sorry, is the line, if it's positive, is it going to be greater than, equal to, or less than 1? Well, if we look, a slope of 1 over 1 from here would be like this, right? It's kind of in the middle. So going up 1 over 1, up 1 over 1, we get us this. So this is less than 1. So our slope is less than 1. It's going to be some kind of fraction. Smaller than 1, greater than 0. Now look over at B. You might wonder yourself, with B, whoa. Oh, it's because the letters are backwards. Okay, this is B. Looks like D on my screen. Actually a B. Okay, if we look at B, you might wonder which one's the line. Well, clearly, this has to be the horizontal axis. And one of these is going to be the vertical axis. It honestly doesn't matter which one. Let's say this one's the vertical axis. The other one's got to be our line. This guy right here. So what's the slope of this line? This red line right here. It's not 0 because 0 is flat, right? But it's perfectly vertical. Undefined. If I look at C, well, it looks like it's going to be positive because it's going up and to the right. So we have positive. And this is clearly very flat. See how it's not like 1 over 1? 1 over 1's like this. Right? So this is, again, less than 1. D. Vertical slope. This is also undefined. This one, clearly negative slope because it's going down and to the right. And if you look, it looks to be going down 1 over 1 each time. This is actually equal to negative 1 for our slope. This last one, again, negative because it's going down and to the right. And it's not very steep. So it's going to be really close to 0. So our slope is going to be greater than negative 1 because greater than negative 1 is closer to 0. So guys, gals, non-binary pals, really important to note this. Right? It's not very steep, so it's close to a 0 slope, right? Here's negative 1, here's 0. Closer to negative 1, or closer to 0, right? Because we're really close to flat, is going to be in here. You see how that's to the right of negative 1? Anything to the right of negative 1 is greater than. So our slope is greater than negative 1. A lot of people say less than because they think like, ooh, closer to 0, small number, right? But it's still greater than negative 1. Olivia, how do we feel about this one? I went through it pretty quick. Oh, okay. 831. The dreaded 831. It should be in the same box with the last problem we did, I think.
Oh, I don't know.
Olivia? The idea is that all the points have the same slope because they're on the same line. That the slope's equal, solve for A. Oh man. Loud. Now when I'm talking, I think it's when I'm doing this. Sorry. Headphone warning. Nice! What about this one? Find the midpoint. Find the point T such that it becomes the new midpoint. 833. So if I know midpoint, that's this, right? The other one is find a T so that Q actually becomes the midpoint. Because originally PQ, find the middle, right? Is what they're asking. Here's PQ, find the middle. Now they're saying, find out what T is so that that Q becomes the middle. Whoops, +3, -6. This is -5, -3. Here's how I think about this. If this is the middle now, how far did we go in the horizontal direction? Well, if I started at -5 and went to 3, I went up by 8, right? Or over by 8, I should say. And vertically, I started at -3 and went down to -6, so I went down by 3. Well, if that's the middle and they're all on the same line, then I should just do that again to find where T is. Right? If I go up 8 to get to here, then I'll also go up 8 to get to here. So if I apply that again, I get 11. And if I apply this again, down 3 again, I'll get -9. That's where T is. Yay. Other one is do midpoint formula to figure that out. That one's pretty easy. Add them up, divide by 2. It's just the average. This one right here, if I add them together, I get -2 divided by 2 is -1. If I add those together, I get -9. -9 divided by 2 is -9 halves. That's the middle, this point right here. Feeling okay about that? Right, literally just do the same thing twice. That'll make this the middle. Cool. 843. Find the equation in standard form of the line that passes through 2,5 and has a slope of 2/5. 843? Yes, do that one? Okay. So, standard form, first off, is this. And A and B have to be integers, meaning no fractions allowed. That's what standard form means. Okay? If you have a fraction for C, so be it. So I know if I've got a slope of 2/5 that my equation is going to look like this. I'll put it in y equals mx plus b. I love that. And I know that it has to go through 2, 5, meaning that 2, 5 is the solution to our equation, right? It'll be on our line, meaning that 2 for x should get 4 or 5 for y. So if I plug in 2 for x and I plug in 5 for y, my equation should be true. So the question is, what does b need to be so that this ends up being true? Well, plugging in 5 for y, plugging in 2 for x, what do I need for b? And that'll give me my equation, which then I'll convert to standard form. So you know how to do this. Times by the top, divide by the bottom. That's 4/5. So what number do I add to 4/5 to get to 5? How about 4 and 1/5? If you wanted to, you could subtract 4/5 to both sides and get that too. That's what b has to be. I'll make that a mixed number, or an improper fraction. So that's 20/5 right there. 21/5 total. That means my equation is going to look like this. 2/5 x plus 21/5. Now we're not done because we need standard form, right? And standard form has x and y on the same side, and a and b, a being this, b being that, have to be non-fractions. So I'm going to times everything by 5. And that'll give me 5y equals 2x plus 21. And then I'll subtract the x over. And there's my standard form equation. So again, don't memorize. Think about process, right? I know my equation has to look like this because that's the slope, right? I know it has to go through 2, 5. So 2 for x, 5 for y. What does b need to be so that it does go through 2, 5? That 2, 5 does be a solution. Well, b needs to be 21/5. Write that out with 21/5 for b. Get rid of my fractions, move things over so it looks more like that. Feeling okay, Olivia? Okay. Find the equation of the line that passes through 0, 9. And has slope -m, where m is the slope of this one. Now, this is in y equals mx plus b form, right? So if this is in y equals mx plus b, that's the slope of this line. So we know that m is the slope of this line. So m is 7. Well, the slope that we need is -m for our line. So if its slope is 7, The slope we need is negative 7. And it goes through 0, 9. So guess what? I know my equation is going to look like this. Because it's the opposite slope of this one. And it goes through 0, 9. That means 0 for x, 9 for y. And some of you at home have already realized that I'm overcomplicating this problem. That's okay. So we have 0 for x. That goes here. And 9 for y. What does b need to be to make this true? Well, 0 times negative 7 is 0. What does b need to be so that this is true? Well, b needs to be 9. Therefore, that's what the 3 dots mean by therefore. So I know my equation is going to be y equals negative 7x plus 9. And that makes sense because if you think about this coordinate, it's the y-intercept, isn't it? It's 0, 9. That's the y-intercept. And we know the y-intercept is just this b value, 9. So now I need the equation that has that slope, goes through that point. I'm done. It doesn't say I need it in standard form. It just says find the equation. I'm done. A lot of you at home would just say, I need this version of the slope, and I know that's the y-intercept, so I need a plus 9 there. I win. Totally fine. How you feel, Olivia?
I think I'm gonna be good.
Okay. 855. This is a proof. It's basically saying that prove if you have something in standard form, you can find the slope super easily with this shortcut. Okay? So it's saying if you have standard form, the slope is just negative a over b. Whatever the negative version of this is over divided by b will be the slope. And we're going to prove that. Here's how you do it. Super easy. If I get this into slope-intercept form, I get the slope for free, right? So what happens when I get this into slope-intercept form? Is my slope going to be negative a over b? Oh, for sure, bud. So if I subtract a, x from both sides, I get this. And if I divide by b, I get slope-intercept form, right? Y is on its own. Oh, sorry. C over b. So this is y equals mx plus b form, right? Y equals mx plus b. Our slope is in fact negative a over b. It always will be. Done. So there's a formula to get slope really quickly from standard form. Apparently it's just this number negated divided by that number. Because that's what happens every time, right? When you change it, that's what will happen. Turns out that's a formula as well for our y-intercept, c over b. But don't need to memorize those, just understand them. 856, Zoe, yes or no? Does every line have both an x-intercept and a y-intercept? No? Olivia? It's super quick. I can do it. Do you need it? Okay. Does every line have both an x-intercept and a y-intercept? Think about that. X-intercepts are where we hit the x-axis, right? That's where we hit the y-axis. Like, you're used to seeing lines like this that have both, right? A y-intercept and an x-intercept. Is there any line that I could draw that would not have both an x-intercept and a y-intercept? So if I do something like that, it only has that y-intercept, doesn't it? And if I do something like this, it only has an x-intercept. So does every line? No. Vertical lines may only have an x-intercept. I use x, I, and t for short. Horizontal lines may only have, getting lazy, a y-intercept. Describe all lines that do not have both an x and y-intercept. We did that. B, if a line has both an x-intercept and a y-intercept, must these two be different points? So up here, see how it has both an x and y-intercept? See how they're different points? Do they have to be? Can you think of a way we could draw a line so that it would hit the x-axis and the y-axis in the same spot? I can. Right? So our x-axis and y-axis, they intersect at the same spot. So yes, a line that goes through the origin, or 0, 0. Work. Cool, done. 861. Yay, nay? What are we thinking? Okay, line L is perpendicular to this graph. So, fun fact, if your slope for one line is 2/3, the line that's perpendicular to it will have negative 3/2 slope. Okay, fun little fact here. So, perpendicular slope is the negative reciprocal of the other slope. And that makes sense, right? Because if I have a line that's like this, it's got positive slope. And if I want another line to hit it at 90 degrees, it needs to have negative slope. So obviously the sign should be different. If this one's going up and to the right, this one's going down and to the right. So again, opposite signs make sense. The steepness of this line will be the exact opposite of the steepness of this line. So do you see how this is the longer side here? It's the vertical side. Or sorry, I should say this is the longer side, the horizontal side. Well, for this line, the longer side for its slope is the vertical side, right? The vertical and horizontal are flipped. So if this is up 3 over 2 to the right, then this is going to be down 3, or not down 3, left 3, and over 2. So these flipped. This is something you guys should have learned in geometry and again in Algebra 1, so I don't have a ton of time to explain why that is, but that's the general idea. So perpendicular slope works that way. So we need a line that's perpendicular to this. So what is the slope of this one? Well, if you think about it, if I subtract 2x and divide by 3, I get the slope, right? Think about it. Move that over. Divide everything by 3. The slope is the number next to the x, so it'll be negative 2/3. So that means perpendicular slope in this case is going to be positive, because they got to have opposite signs. One's going up, one's going down, right? 3/2. And I didn't mean to choose these numbers that are very, very similar here on purpose. It was just me randomly doing it. But that's the slope we need for our line, perpendicular to this. It also has the same x-intercept as this graph. Now remember, x-intercepts. That's where we hit the x-axis, right? What do all those points have in common? Y is 0. Think about it. That's 1, 0, that's 2, 0, that's 3, 0, right? Every x-intercept has 0 for y. So where's the x-intercept? It's where 0 for y. So our x-intercept is going to be something comma 0. So if I do math, I figure out that x is 4 when y is 0 for this equation. So the x-intercept of this equation is 4, 0. Again, think about the concepts. The x-intercept is where we hit the x-axis. If we're hitting the x-axis, our coordinate, half of what we already know, it's going to be y is 0. For this one, it hits it at 4. But we know it's going to be 4, something comma 0, because that's an x-intercept. So I plugged in 0 for y, got x. So we know that our slope is 3/2, and we know our point is 4, 0. So this is very similar to all other problems. We know y is 3/2 x plus b. We know that 0 for y and 4 for x are a solution. It looks to me like we divide that by 2 and get 6. So 0 equals 6 plus b, so b is negative 6. That means our equation is y equals 3/2 x 6. Let's find the standard form. I'm going to times everything by 2 and move things over. 2y equals 3x minus 12. Negative 3x plus 2y equals negative 12 is the standard form. So why this is intermediate and the other one was basic is because basic is like, hey, here's a point, here's a slope. Get it into standard form, right? Here's a slope, but I'm not going to tell you what it is. You got to work for it a little bit, right? It's perpendicular to this guy. And here's a point, the x-intercept. I'm not going to tell you what it is. You can figure it out. And so once you have those, it's a basic problem now. I know the slope is that. I know the point is this. Solve for b. Get in standard. So how do you feel? Sleepy. Feel sleepy. 862. Find an equation whose graph is the line passing through this and is parallel to this. So parallel means they have the same slope, right? So whatever the slope this guy has is the slope our line will have. So let's think about this. Y is almost on its own. If I divide everything by 6, I get 1/6 in front of the x. So our slope is 1/6. Right? If I were to take this and rewrite it, if I divide by 6, I get 1/6 x minus 4/6. So our slope is clearly a 6, right? So we're going to have the same slope. And we're going to have -3, +1 be on our line. So that means -3 for x and +1 for y. And our job is to figure out what b is. If I divide that by 6, I get a half, -1/2 times 1. Or you could do the top. -3 times 1 is -3. -3 over 6 is -1/2. So I add 3 halves to -1/2 to get to 1. So b is 3 halves. You could also add a half to both sides and get 3 halves. So b is 3 halves, which means our equation is this. And it just says find an equation. So did it. Doesn't need to be in standard form. We're done. How do you feel about that one? Yeah? For real? Wait, meh or good? Ah, she admits it. Good. I will recap. Yeah, writing it down isn't nearly as important as understanding it, because if you don't understand it and you go back and look at it, it doesn't mean you're good, right? So, I need an equation whose graph passes through here and is parallel to this one. So what's this guy's slope? Because parallel, same slope, right? His slope will be 1/6, right? And if the slope is 1/6 for them, it'll be 1/6 for your equation, because they're parallel. I need to go through here. -3 for x, 1 for y. What's b? 3 halves. There's my equation. Thanks for asking. We are now in the advanced questions. You want to do them or no? Or go to chapter 3? It is, and I can stay later if you need me to, but I know you guys are like, Jesus Christ, get me out of here. Right? I understand. Your presentation? Okay. Right. Why are you doing this now? Well, you could have done that afterwards. You didn't. You're okay? Okay. So skip to advanced. Okay. Right. So intermediate. Now the good news about 3 is that it's coming back next semester, which you're like, oh God, no. No, it means that's good because 1, you like it more than the other ones. 2, it's mostly Algebra 2 and you like it, which is great because we're doing Algebra 2 next semester, go figure. But also because it means you don't need to get all the check marks to get 100% on it. So you could literally get 100% on 3 without doing a single advanced question, I think. True. Maybe there's one category where you need an advanced question to get 100%. And remember, you don't need 100% to get 100% in the class. Right? This is only 40% of your grade. And so, well, actually, I take it back. You don't need 100% to get an A. It's only 40%. So, oh, I have great news for you. Would you know how to expand that? Then guess what? You know how to expand this. Yeah, and by add on, multiply, but yeah. So this is just going to become x squared plus 3x minus 10. Do you see where I got the plus 3x from? Because I'm going to get negative 2x and positive 5x. I just put them together. Is that okay? Can I skip that step? For sure. So once you get that figured out, right? I got my x's combined. They're 3x's. Right? 5x's minus 2x's. Then you distribute again. So I'll do it in color. That x is going to go to all three. Well, I'll do it this way. X squared distributes to the x, and we get x cubed. Because x squared means x times x. So if I times it by x again, we have x cubed. X times x times x. x squared times 2 is 2x squared. Cool. Now I'm going to distribute the linear term, the 3x. If I distribute 3x, I get 3x times x, which is 3x squared, right? 3 times x is 3x squared. Are you following me on that? And then 3 times x times 2 is the same thing as 6x. And then last but not least, we have to distribute our constant term. Negative 10 times x is negative 10x. And negative 10 times positive 2 is negative 20. And now we just need to combine like terms. There's only one x cubed up here, so it doesn't combine with anything. Right. Do you see how there's 5x squareds here in total? So that's just 5x squared. I have 5 of them. I have 6x's minus 10x's, which is negative 4x's. And then I just have a minus 20, right? Because there's no other constants here to combine. So ta-da. And then don't forget, it says, when will this equal 0? Asking that question now is a bad idea, right? This is a really complex problem. But if you know it's the same as this, and it is, it's really easy. When x is 2, we get 0 times 7 times 4. Well, 0 times 7 times 4 is 0. Winner. When x is negative 5, I get negative 7 times 0 times negative 3. Well, 0 times anything is 0, so I win again, right? And the other way I can win is if x is negative 2, because negative 4 times 3 times 0 is 0. 3 possible solutions. And that makes sense, because secretly this is a cubic equation, because we have 3 for our highest power. So we should have 3 solutions. And we'll learn about that later next semester when we learn about the fundamental theorem of algebra, where it basically says if there's a 3 here, there are 3 possible solutions. If there's a 2 there, there should be 2. Yada, yada, yada. How do you feel about that now? Zoe, did you get this one? 1016? Intermediate 1016. How embarrassing. Intermediate should be in the first box, probably. Oh, no, it might be. It might be in the second. That's what it is. You say, remember the other day I was like, you say something that I was like, stop talking like me in my head. Say, let's take a gander. That's what you do. Say gander. Well, I definitely don't say that. And I don't think you're in danger of me copying you. No, it's not. Look up here, Zoe. Do you know how to distribute? Do you know how to expand that? Yeah. Good, I did. Then you multiply into this. So x squared goes to everything, 3x goes to everything, 10 goes to everything. You get this? Combine like terms. 5x squareds, negative 4x's, negative 20, x cubed. When does it equal 0? Well, when this is 2, because 0 times anything is 0. When this is negative 5, because 0 times anything gets you 0. When this is negative 2, because 0 times I don't care gets me 0. Yep, okay. The 0 problem. Oh, yeah. Can you do these ones, you think? Okay. So this one. First off, we should make it look more like you're used to. I'm going to rewrite this so that it's in order by power. So second power first, first power next, and technically this is the 0th power of x. That's 60. So quadratic linear constant. And I make sure this is positive at the beginning, because again, the more I can make it look like I'm familiar with, the better chance I have of solving it. Now, you might notice something about these coefficients. Remember, coefficients are the numbers that multiply with x. We also technically consider that a coefficient, even though it's really a constant. What do you notice about all 3 of these? What do you notice? So we can divide by 5 to everything. And when we do that, we still get 0, right? Because 0 divided by 5 is 0. 60 divided by 5 is 12. 35 divided by 5 is 7. Don't forget your x. 5 divided by 5 is 1, so we just get x squared. So now this is a problem that like you've seen before, essentially. You know how to solve a problem like this. This is like a basic question, right? If I factor this quadratic, it's easier to answer the question, right? Something times something is 0 is better to answer than all this junk adds to 0. So I know this has to be an x, and that has to be an x, because that gets me x squared. I know both have to be positive because a positive times a positive gets me a positive, and a positive plus a positive gets me a positive. Right? Double negative would get you a positive 12 if you multiply, right? But it wouldn't get you a positive 7. These both have to be positive. What numbers multiply to 12 and add to 7? Well, 6 and 2 doesn't. 12 and 1 doesn't. 3 and 4 does, right? So you know this has to be a 3 and a 4. So if you check it, x squared, 4x, 3x's, that's 7x's. 3 and 4 is 12. Yeah, this is the same as that, which means if you solve this problem, you solve that problem, and I can solve this problem. X is negative 3, x is negative 4. Because when you plug in negative 3, you get 0 times 1, which is 0. And when you plug in negative 4, you get negative 1 times 0, which is 0. Yay! Let's use an algebra strategy for part B. What could we do to make this look a little less nasty? Times by 10, that's one way, and then we have gigantic numbers. There's a better option. You're not wrong, you can do that. Times it by 2, because now we don't have halves anymore, right? So this is really 2t squared minus 19t plus 35. Now, the good thing about a 2 in front of there versus a 10 is that, yeah, I can't just write t times t here, because that won't get me 2t squared. It just gets me t squared, right? If there was a 10 there, I could write 10 times 1. Or I could write 5 times 2, right? There's lots of ways to multiply to 10. But with 2, there's only one way. 2t times t, right? That's why I like 2 better than 10. 2t, yes, very good. I need two numbers that multiply to 35, essentially. And they're either going to be double positive or double negative, right? Because that's how you make a positive. But they need to be double negative, right? Because I'm going to add the 19, or negative 19. So I know that those have to be negative. And before they add the 19, remember, this is going to distribute over to here. So it's going to double whatever I get there, and then add with this one. Because again, this one's not going to double, right? And then get negative 19. So let's think about factors of 35. Well, I know 1 and 35. I know 4, 5, and 7. 6, no. 7, yes, but I already got it. So there are options. 1 and 35, 5, and 7. Now, I want numbers that add to negative 19, so these are all going to be too big, right? So it's got to be 5 and 7. The question is, where does it go? If I put the 7 here, I get negative 14, and I get negative 5. That's the winner. If I put the 5 here, I'd get negative 10 and negative 7, which is negative 17, right? So I'm going to write that down. I'll put the 7 there and the 5 there. I get negative 14 t's. I get negative 5 t's. Total of negative 19 t's. And then when these distribute, I get positive 35. So this is the same as this. Yay. So when this equals 0, that equals 0. Well, I know one of my answers is when t equals 7, right? Because 0 times 9 equals 0. My other answer is this. Let's use our brain for a second. Something minus 5 is 0. What minus 5 is 0? So you know what's under here has to be 5. What do you times 2 by to get 5? Thank you. Because when you times that by 2, the 2's divide out, right? You get 5. So it's 5 halves. Winner, winner. Or 2.5 if you want to think that way, but honestly, that's not as useful. You guys like decimals when they're halves. Why you guys say, I prefer decimals to fractions. No, you don't. You prefer halves to anything if you have to deal with decimals or fractions. And that is true, but there's a difference there. All right. How do you feel about that? Wonderful. We got 4 minutes and then Olivia's got to leave, and she might even have to leave right now. I don't know. Oh, for realsies? Yeah. Oh, that's cute. The only other one that there's like 2 that I think you guys could benefit from. Should I do it really quickly, or are we leaving right now? I understand. This is a long slog. Okay? Is that fine? Okay. Was this beneficial or was it not? True. Yeah, she's period 1.
Wait, when do I take my test?
Wednesday.
It's 1, 2, 5.
Which is why your official review is actually on Tuesday. You can come back to that. Woo, so much fun. You could show up to that. Hang out with everybody. No, I'm going to film both. Do you not want me to film it? I will literally upload it right afterward. Some people don't study until like midnight, so they'll be able to watch it. I wish I was, but I can't be. Actually, no. Normally I am awake at midnight, and then I go to bed, and I wake up at like 4 or 5. Not fun. Someday I will get to sleep. Great. I got to sleep last night. 6 to like midnight, and then like... Nah, that was good. Woo! Yeah! I promise this is normally more fun and engaging with more people here. Okay. Well, I'll turn off the recording now. You can interrupt, but it's for you.